inequality constraints. In this paper, we define two new classes of tree automata with constraints. The first one is a particular case of tree automata with equality constraints. We call it the Hom because we can recognize just languages which are images of regular languages through tree homomorphisms. The second one additionally allows arbitrary inequality constraints. Part of our contribution is to show that these classes are in the sweet spot for dealing with images of tree homomorphisms, because they are expressive enough, but at the same time they have several decidable interesting properties. In order to get an idea of what are Hom equalities, instead of defining them, I just give examples of rules which may appear or not. This rule cannot appear. It allows to check equality of several terms at deeper and deeper positions. This is because the equality tests cross between themselves. At a position, we have an equality test where one of their positions crosses through another equality test. With this kind of rules, emptiness is undecidable. This other rule cannot appear. It allows to check equality of two terms reaching different states. Again, with this kind of rules, emptiness is undecidable. This is a possible rule in a tree automaton with Hom constraints. We are forced to compare equality between positions occurring in the left-hand side and label it with the same state. The left-hand sides of rules are not flat. Thanks to this, we can test the quality of terms at different depth. In this particular case, we can check equality of these two terms and equality of these two terms, but cannot check equality of all them deeper and deeper. For proving decidability of emptiness and finiteness, we need the use of pumpings. They are a traditional concept in automata theory. The idea is to convert a run into another run by replacing a subrun by another subrun. It can be a decreasing pumping in order to decrease the size of the run, or an increasing pumping in order to increase the size of the run. Decreasing pumpings allow to prove decidability of emptiness, since they give a bound for the existence of an accepted term. Increasing pumpings allow to prove decidability of finiteness, since they give a bound for the maximal height of a term in the case where the language is finite. For plain tree automata, the necessary and sufficient condition to ensure that the new run is correct is that the resulting states of the two involved subruns coincide. When the tree automata has equality and inequality constraints, the constraints may be falsified when replacing a subrun by a new run. We prove the existence of such computational bounds when we deal with Hom and inequality constraints. This is done with an involved combinatorial argument, and I recommend to look at the paper for the details. We also show for a given tree automaton with equality constraints how to construct a tree automaton with inequality constraints, recognizing the complementary language of the first. This construction is rather simple, but surprisingly it has not been stated before and has important consequences. Moreover, it is a key point for the decidability of Hom. For listing our results, I denote in this way regular tree languages, a tree automaton with equality constraints, a tree automaton with inequality constraints, and a tree automaton with Hom equality constraints and inequality constraints. Here we have the list of our results. Among them, it is particularly significant the decidability of the inclusion problem for images of regular languages through tree homomorphisms. The decision procedure complements the second automaton, obtaining a tree automaton with inequality constraints, intersects it with the first, obtaining a tree automaton with Hom equality and inequality constraints, and tests emptiness. In the context of XML, this solves the type-checking problem for homomorphic transformations, that is, whether the image of a type is included in another type. Our main result, the decidability of Hom, has also consequences in the context of XML. It solves the question of whether the image of a given type through a homomorphic transformation is also a type. The decision algorithm for Hom has a simple description. Given a tree automaton and a tree homomorphism as input, we first compute a tree automaton with Hom constraints describing the image. Then we construct a tree automaton B by replacing all positions with checked equality occurring in a Hom by ground terms up to a certain depth, which depends on the input. Next, we check whether B still recognizes the same as A Hom. In the affirmative case, it's clear that then the image is regular. The surprising point is that in the negative case, we can conclude that the image is non-regular. The key is based on this automaton. The intersection between A Hom and its complement recognizes the empty set. This seems a mistake when one reads the paper for the first time. But this automaton allows to know which states are not reached by a given term thanks to the complement part. Moreover, these unreachable states are preserved by pumpings. In order to get an idea, suppose we have these rules in a Hom where Q and Q' are accepting states. Suppose we have this run for a big enough term, where we are also marking the unreachable states with the complement automaton. In this case, only the first rule is applicable because Q' is unreachable for the first child, and hence the second rule cannot be applied. Suppose the same happens for the rest of the rules. Then we have infinite pumpings on these positions, that is, infinite elections to put the same subterm at both childs and preserving the reachable and unreachable states. Now, suppose the image is regular and let C be a tree automaton recognizing it. We take a big enough T among the infinite ones we have and combine the execution of C here. Note that the top state of C must be accepting since this term is from the image. Now, we can pump the first child and get different terms at both childs, so that the first rule is not applicable. The second rule is neither applicable since Q' is unreachable in the first child. Hence, this term is not accepted by A Hom, but it is accepted by C, and this is a contradiction. As future work, we will look for simpler arguments in order to make the proofs more accessible. Also, we plan to study whether our new class of automata can be further extended by preserving their good properties. We also want to see the applicability of our techniques for other kind of automata and other topics. And this is all. Thanks for your attention.